Here is part two. I guess I talked too long. My free version just ended. I'll try to speed this up. My apologies. All right, so when I graph this, it is clearly a quadratic function, as discussed in part one, which means that my position time graph is always going to be a parabola. A parabola that swoops up, that is going to tell me that it has, in this case, a positive acceleration. I know it has a positive acceleration because the velocity is getting bigger each second. In other words, the slope is getting bigger each second. This one here, okay, it has swooped down. What's the acceleration here? Well, my velocity is starting big and negative and getting less negative. Oh, this is still a positive acceleration. Visual clue is that this is concave up. It looks like a cup. This is concave up. It looks like a cup. These graphs would make a lousy cup. The water is going to fall right out. That tells me the acceleration is negative. And if you look at it, all right, big positive to small positive, that's a negative change. And small negative to big negative, that's a negative change. So both of these are a negative acceleration, and both of these on top are a positive acceleration. I wonder if I hit that button, if it'll make it big right there. Yay! All right, and then this graph, no one cares about. No one's ever going to ask you to graph this. So moving on. All right, why do we care about all this? Because there are three situations we might be dealing with. All of them are constant acceleration. Acceleration will never change in our problems. But there are three things that it could be. It could be zero, it could be positive, or it could be negative. Let's talk about zero. If we got an acceleration that is zero, and it stays zero, and then it's zero some more, we got three things that could happen to velocity. Either the velocity starts positive and it stays positive forever, or it's zero and it stays zero forever, or it's negative and it stays negative forever. All right? Each of these velocities is going to have an effect on the position. So let's start here with zero. If the velocity is zero, that means the position is going to change by zero every second. So it's going to be constant. Position's not going to change because the velocity says, hey, position, change by zero every second. So it does 1 second plus 0, 1 second plus 0, 1 second plus 0, so on. Here, I got a positive velocity. So that means the position is going to go plus 1 each second. 1 second plus 1, 1 second plus 1, 1 second plus 1, so on. Now down here, I got a negative velocity. That means that it's going to go -5 in this case each second. So 0, 1 second minus 5, 1 second minus 5, 1 second minus 5, 1 second minus 5. Now these position time graphs, the shape is going to stay the same no matter what. Where they are, where they start, does not matter at all. These velocity time graphs, clearly where they start does not matter. They're going to be the same shape no matter what when the acceleration is 0. When the acceleration is positive, the velocity time graph is going to look like this. Again, it doesn't matter where the velocity starts. Here it starts at 0. Here it starts at -10. It does not matter where it starts. It's going to look like that, where the slope of this line is going to be equal to the acceleration. In this case, the acceleration is 1. That means the velocity goes plus 1 every second. 1 second plus 1, 1 second plus 1, 1 second plus 1. And down here, starting at -10, 1 second plus 1, 1 second plus 1, 1 second plus 1, so on. All right, now the effect of these graphs on the position, that's going to be these, which we looked at earlier, if you recall. My position is going to go up just a little bit at first, and then the position is going to go further, and then further, and then further, and further, and further, which with each second, I travel further in 1 second. Whew, that's a mouthful. Because the velocity is increasing. I'm speeding up. Small slope, small velocity. Big slope, big velocity. And then down here, I got big negative velocity, big negative slope on my position time graph. And here, very tiny negative velocity, very tiny negative slope. Never mind. I'll save that rant for when I get back. All right, and negative acceleration. Exactly what we'd expect, except everything is flopped. velocity is going down, which means that the slope is going to go down. The velocity is getting more negative, so I'm going to see the slope get more negative, bigger and more negative. All right, last thing, average versus instantaneous. So if this is my position time graph, the slope at any given point, so that would be the orange lines. Those are my tangent lines. If I could find the slope just right there, that would give me the velocity at that instant. Instantaneous, the velocity at that instant. But if I don't care, if I'm doing bigger calculations, all I need is the average velocity. In which case, I'm just going to take the beginning and the end and make a line. And the slope of that big line will give me the average velocity of the entire motion. So I don't need to actually add up all the velocities and then divide by the bajillion. I can just make one line, find the slope, and that will give me the exact same answer. All right, there we go. Not exactly the short lecture I promised. I apologize. But trust me, that big section about the algebra is going to be helpful when you start looking at those example problems. Thank you very much. I'm done.